The $25 billion eigenvector. It sounds like the title of a sci-fi movie, right? But it's the very real story of how a single, elegant math concept built one of the most powerful companies on the planet. So let's dig in and see how they pulled it off.
$25 billion. That's roughly what Google was worth when it went public way back in 2004. And you know what was at the very heart of that incredible valuation? A brilliant application of linear algebra.
So yeah, that's the big question, isn't it? How exactly did Google's founders, Larry Page and Sergey Brin, manage to turn an abstract mathematical vector into a multi-billion-dollar fortune? To really get this, we've got to rewind the clock to the early days of the internet. And the biggest problem back then was simple. The web was pure, unfiltered chaos. How could you possibly find the good stuff in this gigantic, ever-expanding sea of information?
I mean, sure, in the late 90s, search engines existed, but let's be honest, they weren't very good. As the source material puts it, you often had to wade through screen after screen of links to irrelevant web pages. It was so frustrating. There just had to be a better way.
So, the first idea people had was pretty intuitive. It made a lot of sense on the surface. If you think of the web as a network, why not just set up a simple voting system? But as we're about to see, this simple idea had a major flaw.
The core idea was to treat the whole web like a big democracy. Every single time one page links to another, it's basically casting a vote. It's like it's saying, hey, this other page over here, it's important. Simple enough, right?
To see exactly how this works, let's use this simple little 4-page web as a model. All those arrows you see represent the links, the votes, going from one page to another.
Okay, so if we just count up the votes, the number of links pointing to each page, the ranking looks like this. Page 3 gets 3 links, so it's in first place. Pages 1 and 4 are tied for second with 2 links each, and poor old page 2 is last with only 1. Seems straightforward, but here is the critical, massive flaw. Should a link from some random, unknown page really count the same as a link from a major authority like Yahoo? I mean, intuitively, you know the answer is no. A vote from a more important page should count for way, way more. And that right there is the simple, powerful, billion-dollar idea that became PageRank. Not all votes are created equal. A link from an important page should give another page's score a much bigger boost than a link from some random page. It's not just a democracy, it's a weighted democracy. Now, this brilliant idea creates a really tricky circular problem. And to solve it, Page and Brin turned to a surprisingly elegant piece of mathematics, the eigenvector. Just think about it for a sec. A page's score now depends on the scores of the pages that link to it, but their scores depend on the scores of the pages linking to them, and on and on and on. It creates this gigantic self-referential loop across the entire web. How do you possibly find a stable answer in all that mess? Well, that massive loop is perfectly described by what's known as the eigenvector equation. I know, ax equals lambda x looks a little intimidating, but the core idea is beautifully simple. Think of A as a giant map of every single link on the web. And x is what we're solving for, a list of the important scores for every single page. That list, that x, is the eigenvector. It's the one stable ranking that emerges from all of that chaos. You know, I love this analogy from the source material. It says, imagine you take an object, and you stretch it and you rotate it. No matter how you transform it, at least one line through the object is still pointing the same direction. That direction that doesn't change, that's the eigenvector. For the web, it's the stable underlying structure of importance that holds steady no matter how much you shake everything else up. So let's just walk through it all one more time. The logic goes like this. First, a page's score depends on the scores of its linking pages. Second, this creates that crazy self-referencing system. Third, we can represent that whole system with this one matrix equation. And finally, the solution x that gives us the definitive page scores is, by definition, the eigenvector. And this slide just perfectly illustrates the difference. On the left, you've got the simple vote count, which ranks page 3 first. But on the right, using the eigenvector calculation PageRank, page 1 comes out on top. So why? Because page 1 gets a very powerful vote from the now important page 3. This is why when you search for something, you get a popular, authoritative result, not just some page that happens to have a lot of junk links pointing to it. It's a much, much smarter way to rank. Okay, but there was one more problem. The real web is messy. And this pure mathematical model had a couple of serious shortcomings when you actually applied it.
What happens when parts of the web are like isolated islands? I mean, imagine you have two groups of pages, but there are absolutely no links connecting them. This actually creates a huge issue for the algorithm.
The problem is that it leads to non-unique rankings. The math can tell you which page is most important inside one island and which is most important inside the other one. But there's no way to compare a page from one island to a page from the other. You can't create a single, unified ranking for the whole web.
So, how do you solve this? Well, with another elegant patch that makes the whole algorithm tough enough for the real, messy web. It's called the random surfer model. The solution was to modify the math just a little bit. They essentially decided to take the real web's link map, which is A, and mix in a small dose of a completely random web, which is S. That little m is the mixing factor. And this brilliantly accounts for the chance that a user just gets bored and, instead of clicking a link, decides to jump to a totally random page. And this is what's known as the random surfer model. Just picture a web surfer. 85% of the time, they follow a link on the page they're on. But the other 15% of the time, they get bored and just type in a new address, jumping to any random page on the entire web. This 15% chance is what effectively builds a bridge between all those isolated islands, guaranteeing one single, unique, and stable ranking for everybody. It's genius.
And really, you just can't overstate the impact of this algorithm. The source material says it perfectly. Due to Google's prominence, its ranking system has had a deep influence on the development and structure of the internet. It literally shaped the web we all use today.
This whole story just makes you wonder what other elegant math is out there, quietly shaping our world in ways we don't even see.